The notes seem to start off like super randomly. We're going to talk about assessing a regression line and how to read computer output. And it just starts out with, suppose we randomly select another professional male tennis player. What will we predict for serve speed? This is referencing, and I'm just going to put it up here. You don't have to look at your notes from last time. But this is referencing, in our notes last time, we had data for 14 tennis players. We had how tall they were in inches, their height, and we had their first serve speed in miles per hour. So this question at the beginning of our notes today is just if we were to randomly select another professional tennis player, what could we predict for the serve speed? That means we don't know the height. So how could we make a prediction about serve speed? This is going to seem really random, but one of the things that we could do is just, and it's right here in turquoise, if we don't know the height, go ahead and write this down. If we don't know the height of the new randomly selected player, we could just take all of the serve speeds that we do have and just find the average of those. You're used to seeing X bar, which is the average of the X values, but serve speed here is the response variable. It's the Y value. So in our calculator, we could just have our calculator find the average of list 2, which would be Y bar. And I'm going to demonstrate that for you. I don't really think it's worth your time to type in all the tennis data again. And if you kind of miss it as I'm saying it, or you're not really understanding what you're doing, he'll talk about the same exact thing in the video here in a little while. But if all I know is I need to make a prediction about serve speed, if I add another player in, I don't know their height, so I can't use the regression formula to just plug it in. I could just find the average of all the other serve speeds. And that just says you could do that in 1-bar statistics for L2. Typically we calculate for L1 in the calculator, but you could just make it, you could force your calculator to take your list 2, your Y column, your serve speeds, and it'll give you the readout for that. It'll give you the average of those. It'll also give you the standard deviation, which we're going to talk about in just a second, why that's important. So luckily enough, just look at the screen. I already have those the tennis data still in my calculator from last week. So here's what I would, really the only thing I could base my prediction off of is I could take all of these serve speeds and find the average. So you can do that in your calculator quickly by going to Stat Calc, and again, don't worry about doing this on your own. 1 variable statistics, and usually we just hit enter, enter, enter. Well here, I would want to change that out for list 2. Don't worry about how to do that, I'm just demonstrating it for you, okay? I'm going to switch that out for list 2. And then on my summary statistics page, here is the average serve speed.
Do I need to receive this or what can you receive?
Because I don't have the... Thank you so much. It's exciting. Here's the average serve speed, okay? So if you wanted to write this down in your notes, that's what I would probably predict that this new player would be around that same serve speed, okay? But the question up here also says, how far off should we expect our estimate to be? That is leading you into looking at standard deviation, because standard deviation is how far away from the mean are we typically. So you can write this down. I'll read it out loud because I know it's kind of small. Let me zoom in just a tad too if I can. If we use this as our estimation, if we use that 118.4 miles an hour as our estimation, if we use Y bar, we will typically be off by about, and here's what I'm looking at to get this random number 6.81. I'm looking at the standard deviation of the serve speeds. So it would typically be off by about 6.81 miles per hour. We're about to find out this isn't really an accurate way to make a prediction. To just take the average of all of the data values for serve speed and just assume that no matter how tall a player is, that their serve speed would be about 118 miles an hour. So it will typically be off by about 6.81 miles per hour. And where I'm getting that from is that's the standard deviation for list 2. You'll see this again in the notes later. That's S sub Y. Instead of S sub X, I'm talking about the Y column, so that's the standard deviation of the Y values. And you'll see that S sub Y at the very end of the notes again today. So just want you to know that it's not a random thing. So I followed all the steps you've been through before. I just did it for list 2 instead of list 1. And we're saying that we could use this to kind of make a prediction about this new player. Okay. Then comes the question. We could do that, but how much better would our predictions be if we used height to help predict speed, rather than just using the mean speed? There are 2 ways that you can answer that question of how much better our prediction would be. S and R squared. So we're going to talk about what each of those is, how to come up with those values, and how to interpret them, how to write a sentence about them. Let's first start by talking about S. S is the standard deviation of the residuals. You will not ever need to calculate that either by hand or even in the calculator. That will always be given to you. If the question is referring to S, S will be given to you. So let's just write down. S measures the size of the typical residual. That's what S is. It measures the size of the typical residual, or how far away, remember what a residual is, the actual value is from the predicted value. It's how far away the actual value is from the predicted value. And S measures that on average. It's kind of like the standard deviation just in general. How far away things are from the mean on average. S is the standard deviation specifically of the residuals. How far away those predicted values are from the actual values on average. You won't ever need to calculate S. You don't need to find it in the calculator, so write that down. You will be given S if you need it to answer the question. You will be given the value of S if you need it to answer a question. So those questions would typically be about interpreting the meaning of S. And here's how you would interpret it. I'm going to give you a little sentence frame. If they tell you that on this tennis problem, if S is 5.96, here's what you would write. The typical, the actual, gosh darn it, the actual, and then you're going to put your response variable. Here that would be serve speed. The actual serve speed is typically about whatever S is, and I'm telling you for the tennis problem it's 5.96. 5.96 for tennis data. So the actual serve speed is typically about 5.96 miles per hour away from the value predicted by the least squares regression line using x equals, and for here it would be height, but that's where your explanatory variable would go. I'm going to give you a second to write it down, try to wrap your mind around it. S just tells you that the actual value of y is typically about this many away from the predicted value when you use the least squares regression line with x as the explanatory variable, whatever that is in context. So again, for the tennis data, it would be the actual serve speed is typically about 5.96 miles per hour away from the value predicted by the least squares regression line using x equals height in inches. I'm going to tell you more about S in just a second, but this is how you interpret the meaning of S. Now let's talk about R squared. It's called the coefficient of determination. We've talked about R, and that's just correlation. And you've noticed on your screen with A and B, the slope and the y-intercept, and R, there's also an R squared value. And yes, it's just R squared. But what is it? What does it tell us? It's the coefficient of determination. And if, I'm going to go ahead and tell you for the tennis data, R squared is 0.2856. And I can prove that to you really quickly by going to stat calc linear regression, just like you did on your quiz a second ago. That's not it. We want actually that to be list 1. Okay, there it is. There's my wire out of me here. So here's R squared. You can get it on your calculator, but what does it mean? And here's how you would interpret this, okay? And he'll go over this again on the video, so write it down and then I'll play the video and hopefully it'll make more sense to you. What R squared tells you is that about, and you're going to put R squared as a percent here. So I would say about 28.56% of the variability in the response variable, about 28.56% of the variability in serve speed is accounted for by the least squares regression line using x as the explanatory variable in context. We're looking at the tennis data, about 28.56% of the spread, if you want to think of it that way, variability in serve speed is accounted for by the least squares regression line using x equals height in inches. That may not make sense to you at all right now until you see it illustrated in the video, so just hang tight. This sentence structure shows up on the test at the end of this unit. It'll tell you an R squared value and it'll say, what does that mean? Pick the answer choice that has it written just like this. So if you can see what R squared is, it's really the interpreting of that that's going to be important. And then that last little bit on this page 1 is really important. How is R squared related to R? How is R squared related to S? Well, R squared, you can probably figure out, is just the correlation squared. R squared is correlation squared. If you are given R squared, then use this knowledge, take the square root of R squared, positive if the slope of the line is positive, negative if the slope of the line is negative. Now, you know that. If you take a step back and remember R is, it shows strength and direction. So if R is positive, then you've got an increasing trend, which means the slope of the regression line is positive. If as X is increasing, Y is decreasing, you've got a negative association there, so the slope would be negative, R would be negative because it addresses direction. That's how R squared is related to R. Now, how is R squared related to S? This is really important, and to me, this kind of ties it all together. If you have no idea what we've been talking about all day, R squared and S, here's why we value them in statistics. They both measure how well the least squares regression line, both measure how well the least squares regression line models the data. In other words, it shows how much scatter there is from the least squares regression line. It tells you, are things pretty closely aligned with that linear model, or are the departures pretty far away from the line? It'll measure how well the linear model fits the data. Here's what you're looking for. If I was a student, this would be really, really important, okay? And this might be on a test. You're going to have to use this on the test as well. If you're given R squared, be able to find R. We'll practice that on the back of the notes if you're concerned about how to do that. But right here, just know that you're always looking for a small s value. You want a small s value. The smaller s is, the better, because again, if you really know what s is, it's the standard deviation of the residuals. You want that to be as small as possible. You want the departures from the real line, prediction line, to be small. And you want a large R squared value. The larger R squared is, the larger the square root is going to be, which is going to show more strength in correlation. So that, to me, is what I would want to take away. The most important thing is S being small is good. R squared being big is good. They both measure how well your linear model fits your data. But I just want you to know that neither one of those, neither S nor R squared, address form. You can have an S value and an R squared value, and your data should still not be fit to a linear model. The same thing we talk about with R applies to S and R squared as well. I'm going to pause my teaching and show you this video, and he'll illustrate the same exact things that I've just covered. So just watch. Maybe when I explained it, you didn't quite get it. Hopefully he can help you.
Determination, also known as R squared, and interpreting computer output for regression. So what exactly are we going to learn today? We're going to learn how to determine the coefficient of determination, R squared, how we interpret it, and how we interpret computer output for linear regression. Let's look at an example. This is a context we've used previously, and this was a graphic of a random sample, 11 students in Texas. It charted both the percent of school days they attended as the X variable and the number of questions they answered correctly on the state Algebra 1 test at the end of the year as the Y variable. And when we look at this, we want to ask, how well does attendance predict test scores? How well can we predict test scores using just that variable of attendance alone? Well, one way to frame that is, how much better are the least squares regression line predictions than a model that couldn't use attendance in its predictions at all? So how much better are our predictions using our model that uses attendance than a model that can't use attendance? Well, a model that can't use attendance might work like this. If we're looking at the number of questions they scored correctly on the exam, we can find the mean of that. The mean of those values is 41.3. That's the average number of correct answers on that exam.
That's like when we just wanted to predict if a new tennis player, like what their serve speed would be, and all we had to go off of was all the other serve speeds, okay?
And so if we're making a model that can't use percent of school days attended, simple one to choose is the model where for everyone, we just predict the mean. We predict you would get 41.3 questions correct on average on this exam. And so we're going to make that our model. Y hat, the predicted Y, is going to be the mean Y value. Because again, we can't use a function of percent of school days attended, so we're just going to predict that mean for every data point. So again, this is our model, and we're not allowed to use X, the percent of school days attended, to make predictions. So we get the residuals here to see our prediction errors. And we can square those to get rid of any negatives and to get a sum of squared residuals, which is how we usually evaluate our models.
Here is the first time you actually see illustrated, and I wish I had been able to show you this last period, last class. You can actually see this squared residual thing illustrated. I think it's really helpful. So if you take all the residuals and you square them to keep them positive.
And we see this is a terrible model. There's a lot of error. Those huge boxes, that's a large squared residual.
When you add the area of all of those squares together, you're going to get a really large number. And that means that this model, this green line, was not very good.
This is a terrible model. It's probably going to be a lot better if we do some sort of function of percent of school days attended to make a better fitting line, better fitting model. And that's what our least squares regression line is. It's a model that uses a function of the percent of school days attended to fit a line that minimizes the sum of squared residuals. And this is the model where we actually use X to predict Y. So here are residuals under this
Look how
model.
much
Here are the
smaller.
squared residuals. You can see a lot less area there. So this is a good model. There's little error. How much better is it? Well, that's where we're going to come in with a comparison. So comparing this model, our least squares regression line, to our simple mean model, you can see a pretty big difference. Again, least squares regression, mean model. Least squares regression, mean model. Big difference. How much bigger? Well, we're going to look at that in a second. And it's clear that when we use X, we get much better predictions. So here is visualized the sum of squared residuals under our mean model versus under our model that used a function of percent attendance, our least squares regression line. And we can see a huge reduction in the sum of squared residuals. The exact percent reduction is here, 90.3. So using X in our model, using the percent attendance as a predictor, resulted in a 90.3% reduction in the sum of squared residuals. And that number, 90.3%, is what we call the coefficient of determination, R squared. So R squared is the percent of variation in the response variable that is explained by the explanatory variable in the model. And here's a template for interpretation you can use of R squared with the least squared regression line. So in our case, 90.3% of the variation in the number of exam questions answered correctly can be explained by the linear relationship with attendance rate. So here's a fun fact. The coefficient of determination is equal to the correlation squared. And what that means is the coefficient of determination is equal to the correlation, which we said was R, the R value, squared. And the coefficient of determination is R squared. So R squared is equal to R squared. What What? Yeah. To find r squared, all you need to do is take the correlation, the r value, and square it. That gives you coefficient of relation r squared. Pretty simple. And here's some properties of r squared. R squared is always a number between 0 and 1, or 0 and 100% if we're using percents. R squared closer to 1 signifies a stronger
Same thing
relationship,
that
and
we
r
talked
squared
about
values
with
closer
r
to
is
0
r
signify
squared.
a weaker relationship. Now, let's talk about some of the ways that you might see r squared in other components of a least squares regression line model.
Okay, what he's going to talk about next is turn your paper over. Page 2 of the notes. He's just going to talk about what I have on your notes here are 2 different ways that you might see a computer output. Like literally on an AP exam, they might give you a little box where it's got a computer readout, and you have to take all of that junk right there, and you have to figure out the slope, the y-intercept, s, which I think is pretty obvious because it says s equals, and r squared, which I think is pretty obvious because it says r squared. But where do you find the y-intercept and the slope? So listen to his explanation of this, and I think we can do it before lunch.
Given to you. We're talking about computer output. For this least square regression line, if you were to model it using statistical software, you might get a table like this from the software you would use. This looks very complicated, so you might be confused at first, but let's break it down, because if you're going to be doing this work in statistics, you're going to see a lot of these. So remember, our least square regression line is made up of 2 components, a y-intercept plus a slope value. So notice that the y-intercept is a constant in our model, and the slope value is the coefficient on x. And if you look at our computer output, it's easy to identify where the x variable is. Attendance. Attendance was our explanatory variable in our model. And so the slope value is the coefficient of x, attendance. That's 0.57. And the constant is our y-intercept, in that case, negative 7.69. So taking that computer output and putting it directly as our model, y hat, the predicted y value, is equal to negative 7.69 plus 0.57x.
Okay, look at this really quickly. It's going to be the same on every single computer output that you see. The number next to constant is going to be your y-intercept. So at the top of page 2, that first computer readout up there that does not have a box around it, what's the y-intercept? 12.0513 is the y-intercept. The slope is always going to be right underneath that because it's the coefficient of the x variable, which was height when we talked about tennis. So what is the slope on that computer readout at the top of your page? Yeah, somebody said it, that 1.4103. What is S? It literally, yeah, don't overthink it. It says S equals 59.5. And what is R squared? That's 28.6 or 0.286. Don't look at the R squared adjusted value. When we get back from lunch, I'll have you write all of that down, and then I'll show you some formulas to end the notes. We just want to make sure that if we're given a computer readout on a test, we know where to locate the y-intercept, the slope, so that we might be able to take this and write the equation for the least squares regression line. These are going to be your important numbers for least squares regression line. The constant, that's going to be your y-intercept. And then the coefficient of the x variable, and in the tennis data that was height, that is your slope. Here is where they are giving you an S value, so they could maybe ask you something about S. And then R squared is given, which would also equate to 0.286. So a couple things I want you to be able to do with this. I would want you to be able to write the equation of the least squares regression line, which is y-intercept plus the slope times x. Well, the slope is positive 1.4, so I'll put positive 1.4103x. That's the equation of the least squares regression line. I want to make sure that you could use this computer readout to find the correlation, which again will tell you strength and direction. So you're going to take this r squared value and because the slope is positive, r will be positive, and all you need to do is take the square root of r squared as a decimal is 0.286. Just in case it gave you this computer readout and asks you any questions about r. So in your calculator, you just do the square root of 0.286, and you get an r value of 0.53. Let's quickly do this. Here's a different computer readout. So you can just see that it's the same exact information given to you in the same way. 16.3 is the constant. We're comparing zinc and lead levels here for something parts per million, but that 19.0 is the slope. So you should be able to quickly use those pieces of information to write the equation of the least squares regression line. And have the skill of finding r. Again, this example, the slope is positive 19. Your r value has to be positive then. That's over here, this coefficient of lead was a negative number, then the r value would be negative. And I'm using that 0.82. Higher r squared value is desirable because that means we're going to get a higher r value when we take the square root of 0.82. So r squared is the coefficient of determination. R is just correlation. That's what their names are. And here we can see we've got some strength. Okay, the last little bit of the notes here, I'm going to tell you this information, then I'll play a short, I think 4-minute video of him saying the same thing. How could you calculate the equation for the least squares regression line using just summary statistics? That would be like, look at this problem that is posed at the bottom of your page. If I told you the average of the x values and their standard deviation, the average of the y values and their standard deviation, and r, how could you come up with the line of best fit, the least squares regression line? There's two formulas here that you're going to want to be comfortable with, and they're not mind-blowing. To find the slope of the least squares regression line, you're going to take r and you're going to multiply it by this fraction, the standard deviation of the y values over the standard deviation of the x values. And before you freak out on me, those will be given to you. If you want to find the slope, take your r value. Now r is either just going to be straight up given to you, or you might have to derive it, bless you, from r squared. You might have to take the square root of r squared to get your r value. You'll just multiply that by the fraction of the standard deviation of the response variables over the standard deviation of the explanatory variables. Those will be given to you. It's really easy. That's how you come up with the slope. Well, the two things you need to write the equation of the line is you're going to need the slope and you're going to need the y-intercept. So he does a really good job in the video of illustrating this for you, but I'm going to show you something really fast. The average of the y values is always going to be equal to the y-intercept plus the average of the, the slope. Hang on, I got to erase that. B in front of x bar there. The slope times the average of the x values. This looks exactly like y hat, but instead of y hat, it's the average of y's, and instead of the x value here, it's the average of the x's. He's going to explain in the video why that is. Well, big picture is, how could I write the equation of the line? Well, here's how I could get slope. If you want to get y-intercept, check this out. just solve this equation for A. That means y bar minus the slope times x bar, and you'll have your y-intercept. We're going to practice that in just a second on this the bottom of the page. The reason this works, and he'll explain it and he'll show it to you, the reason this equation holds true is because the least squares regression line always goes through the point ordered pair x bar, y bar. I don't think that's a significant thing for you to understand. As long as you can remember the formulas to get your slope and your y-intercept, you should be good to go. Let's practice that right now. So you'll see a test question like this. Calculate the equation of the least squares regression line. Here's x bar, here's the standard deviation of the x's, here's the average y and the standard deviation of the y, and the correlation. So the first thing I'm going to need to figure out is the slope. So I'm going to take r and multiply it by standard deviation of y over standard deviation of x. Everything's given to me this time, so it's really easy. That's 0.49 times the fraction 12.7 over 2.3. We end up with a slope of, take a second and crunch the numbers, make sure you're comfortable with that. We get a slope of positive 2.71. It's positive. You can't ever have a negative standard deviation, so the only thing that would end up making the slope negative is r being negative itself. Then I need the skill of finding the y-intercept. And if I want to find the y-intercept, right up here it says I do this. I take y bar, subtract b times x bar from it. Y bar is given to me as 104.9. I just found slope, so before I can do this, I would have to find the slope and multiply it by x bar, which is given to me as 12.3. .9 minus 2.71 times 12.3, 71.63. I can finally put everything together, and here is my least squares regression line formula. The predicted value of y is equal to the y-intercept of 71.63. I'm going to put a plus sign because my slope was positive, 2.71 times the response variable, times the explanatory variable x. Here are the big takeaways of the day. Know this formula to get your slope. Know this formula to be able to find your y-intercept, which you have to find slope beforehand. Know that s and r squared are both measurements of how well the linear model fits the data. Know how to find all your stuff in a computer readout. Know that a smaller s value is desirable, a larger r squared value is desirable. And then just know your sentence frames for being able to interpret s and r squared in context. If you know those things, you guys, then you're good. Homework will let you practice those things, so be sure you're actually doing your homework. And that is it.